In this video, we're going to look at solving stoichiometry problems where at least one of the reactants or product is measured as a solution volume rather than measuring all of our quantities by mass. So first of all, let's look again at what the meaning of molarity is. It's going to be how we know the quantity of solute in terms of moles is present in a given volume of solution. Now, while we measure quantities of solids in a lab using mass, typically we'll measure volume by liters or milliliters. Now, for solids, we had a very nice conversion factor, the molar mass, which gave us the relationship between mass and moles. But when we're measuring quantities of liquids and solutions in the lab using volume, what we need is a relationship then between volume and moles. And that's going to be for solutions the unit of molarity, which we'll abbreviate with a capital M. But what molarity means is the number of moles of solute that are present in each 1 liter of solution. So for example, if I have a 0.450 molar NaCl solution, and M is red molar, that means I have 0.450 moles of NaCl present in each 1 liter of that solution. So molarity then can be used as the conversion factor, which will give us the relationship between the quantity of moles of solute that are present in each liter of our solution. Before we get to our stoichiometry problem, let's just look quickly at a solution molarity calculation problem. So for this problem, what we want to do is to find the mass of sodium chloride, that will be a solid, needed to make 250 milliliters of a 0.850 molar NaCl solution. Now, molarity will allow us to convert from volume to moles. So the molarity here is a relationship between the volume in liters of that solution and the number of moles of sodium chloride that are present. And then, since we're going to be needing to know the mass of sodium chloride, we can use molar mass to convert from moles to mass. So this will be a 2-step conversion factor problem. First of all, let's look at the relationship between mass of sodium chloride and moles. That comes from the molar mass. So 1 mole is going to be equal to 58.443 grams. That comes from the calculation of molar mass for NaCl. We've done calculations of molar mass of solids a number of times, so I won't repeat that here. But remember, whenever I have an equality relationship like this, it means I can set up 2 possible conversion factors. I can put mass over moles, as I did here, or moles over mass, and each of those would be equivalent. I can use the appropriate one when I need to do the conversion between mass and moles. Now for the solution, the 0.850 molar NaCl, what I know from the definition of molarity is that there's 0.850 moles of NaCl in each 1 liter of solution, so I can write that as an equality. From that, I can generate 2 conversion factors. I can put moles of NaCl over liters of solution, or I can put liters of solution over moles of NaCl. And again, I can select the appropriate one when the time comes. So let's set up our problem. We're going to start with the given information. The quantity we're given is 250 milliliters. Now, notice that when we use conversion factor, molarity is a conversion factor, that the unit is not milliliters per volume, but liters. So one of the first things I need to be able to do is to convert my milliliters into liters. So that we can simply move the decimal 3 to the left, and our 250 milliliters becomes 0.25 ml. Or, our 250 milliliters becomes 0.25 liters. So that's our starting information. So let's put that in first. The first step will be to convert the volume of that solution into number of moles of NaCl. For that, I'm going to use the molarity as a conversion factor. I want to cancel liters and keep moles. So for that, I'm going to select this particular conversion factor. Liters in the bottom, moles in the top. My liters then cancel, leaving me with moles. So that tells me how many moles of sodium chloride I need. but what I'm interested in is the mass. So the next thing I need to do is to convert that moles of sodium chloride into mass. I want to cancel moles and keep grams. So I'm going to select this conversion factor, moles in the bottom, grams in the top. When I write it this way, the moles cancel. And then I can do the math. 0.25 times 0.85 times 58.443 divided by 1 again. And that equals 12.4 grams. So that's the quantity of sodium chloride I would need to make 250 milliliters of a 0.850 molar NaCl solution. Well, let's take the next step of solving a stoichiometry problem, again using molarity as a conversion factor, much like we've used molar mass in the past. So in this particular problem, I want to find the mass of lead bromide precipitate, that's this product here, that can be collected when an excess quantity of 0.500 molar sodium bromide, that's this reactant, I have an excess of that, is going to be mixed with 50 milliliters of 0.100 lead nitrate. That's my other reactant. So because I know I have an excess of sodium bromide, I know that my limiting reactant is going to be lead nitrate. So that just comes from the wording of the problem. Now, my starting information is the quantity of that solution I have. Now notice it's not expressed in grams, it's expressed in milliliters. But for me to use molarity as a conversion factor to convert that milliliters into moles for lead nitrate, I need to first convert that milliliters into moles. So I'll do that, move the decimal place 3 to the left. And when I do that, I get 50 milliliters equals 0.500 liters. So let's start there. The other thing I'm going to need is eventually I'll want to convert my number of moles of lead bromide into mass, since that's what I'm ultimately after. So again, I won't go through the calculation of molar mass. We've done that a number of times, but just express the result here. There's 367.008 grams in each mole of lead bromide. So let's start with the starting information. I know that if I had everything expressed in moles, it would be very simple because I know the mole ratios between lead nitrate and my product. Each of these has a assumed coefficient of 1 in front of them. So I know that each 1 mole of lead nitrate can be converted into 1 mole of sodium bromide, or lead bromide, a 1-to-1 chemical reaction ratio. However, I don't have my reactant measured in moles. It's expressed in volume of a solution. So let's start with the quantity that I know. That's going to be expressed in liters. And once I know that, I'm going to use the molarity of the solution to convert to moles. So the first conversion factor uses that molarity. Then I'm going to convert from moles of lead nitrate to moles of lead bromide. And at the end, I'll take my moles of lead bromide and convert that into mass. So let's start with our starting information. There's the 0.5000 liters of lead nitrate. I want to use my 0.1 molar information, moles over liters, or liters over moles. I want to cancel liters and keep moles, so I'm going to use that molarity as a conversion factor with liters on the bottom and moles on top. So I put 0.100 moles over 1 liters, the liters then cancel. That tells me how many moles of lead nitrate I'm starting with. That in turn, using the 1-to-1 ratio between the moles of lead bromide, again, 1 mole understood here, 1 mole understood there. I want to cancel moles of lead nitrate and keep moles of lead bromide. That tells me how many moles of lead bromide I should be able to produce. The last step then would be to convert that to mass. I'll use molar mass as a conversion factor. I want to cancel moles and keep grams. So moles will go on the bottom. Then we can do our calculation. So let's start on the far left with 0.0500, then times 0.1 going across the top, times 1, times 367.008, and then along the bottom, divide by 1 again, divide by 1 again. When I do all of that math, what I end up with is a final answer of 1.84 grams of that lead bromide product that I should be able to produce given my starting 50 milliliters of 0.100 molar lead nitrate. Now again, I want to express that in 3 significant figures. The reason is because my